Welcome to a new season of Nova Science Now. I'm Neil deGrasse Tyson, astrophysicist and your host. In each show, we'll bring you several stories, breaking news from the frontiers of science. You'll meet my fellow scientists exploring the universe, from the tiniest microbes to the farthest reaches of the cosmos. First, let's take a look at our own solar system. It can seem like an orderly place, where the planets chug along in their orbits like trains on a track. But there's no guarantee those tracks will remain clear, because in addition to the planets, there's a lot of other stuff in the solar system, and eventually their paths will cross. Now, if you happen to live on one of those planets, that would be bad. One night in 2004, telescopes spotted a tiny dot moving across the sky. That dot was actually an asteroid named Apophis, and it seemed to be headed towards Earth. When seen even through our most powerful telescopes, Apophis shows up as nothing more than just a moving speck of light. But the latest data tell us that this asteroid may be as wide as 1,000 feet. That's bigger than the Rose Bowl. Now imagine that hunk of rock hurtling through space on a collision course with Earth. It sounds like something from the movies. Remember Deep Impact? Or Armageddon?
Rise and shine!
Where Bruce Willis saves the world? The movies were a little silly. Somehow all the flaming fragments in Armageddon had good aim and hit only famous buildings. But they were inspired by a basic and frightening truth about our solar system. It's easy to think of the solar system as a big, wide open playing field. The sun in the middle and just a few planets in orbit around it. But in fact, between the planets, it's filled with debris. Of all sizes, some as small as a pea, others as large as cars, houses, even mountains. We've been hit before by these things. And you know something else? We're gonna get hit again. In space, they're just cold hunks of rock. But when they plunge into Earth's atmosphere at 30 or 40,000 miles an hour, their surface glows red hot. Small objects will burn up before hitting the ground. We call those shooting stars. But the bigger ones will keep on coming and explode on impact. If you know where to look, you can see the damage caused by past impacts all around us. Our moon is scarred with countless craters. Here on Earth, this mile-wide hole in the Arizona desert was blasted by an asteroid as big as an office building. And 65 million years ago, a rock the size of Mount Everest slammed into the Yucatan. That's the one that triggered the demise of the dinosaurs. Our long history of getting in the way of asteroids worries Apollo astronaut Rusty Schweickart.
I mean, an asteroid can literally destroy 80 or 90% of the species that are alive on Earth. These are big events. I mean, this is called extinction.
To guard against catastrophe, a team at NASA tracks asteroids, including that potentially lethal one, Apophis, named for an Egyptian god of darkness and evil.
It was clear that it was going to be a very close approach and fascinating object.
In late 2004, with just a few observations to go on, the team came up with a scary prediction.
Very often, they started 1 in a million, maybe even 1 in a billion. In this case, the maximum probability was about 1 in 37.
1 in 37 chance that in April of the year 2029, Apophis would slam into Earth on, get this, Friday the 13th.
Never seen anything like that before. That was absolutely extraordinary.
Extraordinary indeed, but not necessarily right. The NASA team has to continually revise its predictions.
It's much like predicting a hurricane. When it's first spotted, you don't know where it's going to hit. As you get more and more information on its track, you can predict where it's going to go.
It turned out that Friday the 13th, 2029, wouldn't be so unlucky after all. Apophis will not hit us that day. But the asteroid will come frighteningly close to Earth.
It's going to come 10 times closer to us than the moon is. So it's actually going to pass closer to us than the ring of satellites, communication satellites that are in synchronous altitude around the Earth.
Such a near miss means that Earth's gravity will dramatically alter the asteroid's orbit. Problem is, as its path bends, there's one small region of space we do not want Apophis to pass through. Chodas named it the keyhole.
If it should pass through that little keyhole, then it would be on a collision course at a later encounter. Now, if I advance it after 2029, you can see...
If the asteroid passes through the keyhole, then 7 years later, in 2036, Apophis will be headed right for us.
Zoom in on the Earth.
So what if that one possibility actually happened? What kind of damage could an asteroid the size of the Rose Bowl do?
If Apophis did impact, it would impact at around 7.5 miles per second. And all that energy has to go somewhere. It would leave a blast area of around 60 to 100 miles across. And it would dissipate energy about equal to 100 nuclear bombs going off at the same time.
An asteroid the size of Apophis, if it hit land, could devastate several counties in, say, Southern California. But if Apophis passes through the center of the keyhole, it will slam into the Pacific Ocean, nearly 1,000 miles off the California coast. And that could be a lot worse.
If it hits in the ocean or in the water, it's going to create a very significant tsunami. Right.
I met up with Rusty Schweikert to find out what that tsunami might do to Santa Monica Beach.
We would have 3.5 hours of waves 55 feet high and larger crashing onto this shore.
So not just a simple rise in the water level that we saw in the Indonesian tsunami.
Right.
You're talking about a surfable wave.
That yellow building will be gone.
Mm-hmm. So it's basically going to chew its way into the coastline.
It's going to sandpaper the whole coast all the way up and down from the Panama Canal all the way up to Alaska.
So if this or any other asteroid has our name on it, do we just run for our lives? Or could we actually do something about it?
Unlike any other natural disaster, especially the big natural disasters that we know of, this one, if we use our brains, we can prevent. We don't just prepare for it, we can literally stop it from happening.
What you're saying is we don't know how to turn off a volcano yet. We don't know how to undo a hurricane.
That's right.
This is one of the great natural disasters that we have the power, the knowledge, the means of avoiding.
Astronauts!
In the big asteroid movies, the solution always seems to be the same. Send up some action heroes
God be with you.
and nuke the thing.
That's a very, very bad way to try and deflect an asteroid that's headed for the Earth. You're going to certainly have a lot of debris. So that stuff is going to end up hitting the Earth anyway. You don't know what's going to happen.
But if nuclear weapons aren't the best defense against asteroids, what is?
If it's a small object, you could simply run into it, slow it down or speed it up so that in 20 or 30 years, when it was predicted to hit the Earth, it would be slowed down just enough that it would miss the Earth, or sped up just enough that it would miss the Earth.
Just recently, NASA slammed a spaceship into a comet. They weren't trying to deflect it, just study what it's made of. But before you could successfully deflect the hunk of rock like Apophis, you'd have to know its exact shape and structure. Lance Benner studies asteroids with radar by bouncing radio waves off the rocks.
Radar imaging of asteroids has revealed a completely bewildering zoo of different shapes and sizes. We see objects like this one that's roughly the shape of a cucumber. We see many that look like potatoes. We're seeing a surprising number that are actually spheres.
There's even one that looks like a dog bone. And what about Apophis?
We know very little about Apophis, unfortunately. We have a crude estimate of its size. We don't know anything detailed about its shape. We don't know if it's a porous object.
Deflecting a weirdly shaped or porous object would be a challenge. A more flexible solution might be a gravitational tractor. The idea is, send an unmanned spacecraft up to the asteroid and have it fly just ahead of the rock. Then, the spaceship's gravity can, over time, work to subtly change the asteroid's speed, putting it on a slightly different orbit.
If you use a gravitational tractor where you're pulling it using gravity as a tow rope, you know precisely what you're doing and what's happening to the asteroid all the time.
For Rusty Schweikert, the consequences of failure are so dire, he believes NASA needs to demonstrate this technique now.
I think the world public is going to want to know for certain that something is going to work when you go up and try to, deflect an asteroid from wiping out life. They're not going to want to hear a bunch of scientists say, well, we think it'll work, or it's 80% probability, or 95% probability. You're going to want to know.
So, out of all of those cases...
Not everyone thinks we should be spending a couple of $100 million on a deflection mission anytime soon.
I'm of the opinion that the majority of the resources that NASA is devoting to this effort should be in searching for these objects and finding them early.
We know of about 4,000 near-Earth asteroids, but recent estimates tell us that there's thousands more just as deadly that we have yet to discover.
An object like Apophis is just the tip of the iceberg. So my concern is not with this individual object. My concern is the tens of thousands of these objects that we haven't yet discovered, and that could take us by surprise if we don't discover them.
Okay, remember this thing? That mysterious chart of boxes from chemistry class? Of course, it's the periodic table. It lists all the known elements, like hydrogen, gold, calcium, aluminum, and even down here, Einsteinium. And what makes an element unique is the number of protons each atom contains. We call that its atomic number. The table starts up here at 1 and keeps going and going and going. But way down here, it just stops. What's up with that? Why can't we just add more protons to an atom and build new elements? Well, correspondent Carla Wall has found some folks who spent their lives trying to do just that.
Every atom in the universe was born in fire. Oxygen, iron, neon, copper, carbon. The fundamental building blocks that make up all matter, all things, were created with immense heat and pressure. By the Big Bang, stars, or sometimes by scientists like Ken Moody.
I don't feel very stellar, I guess.
He does, however, rise before the sun each morning and gets to work by 5, 7 days a week.
That's the way it is.
He's a nuclear chemist whose passion is filling in the blanks at the upper reaches of the periodic table.
Pop quiz.
The chart of elements.
Number 44.
Ruthenium.
Oh, very good. 109.
Meitnerium.
Very good. 114.
Unnamed at this point. You're not going to trick me.
The trick, as Ken sees it, is to be the one to name 114, which he's been on a quest to discover for more than 2 decades.
We tend to call these things discovery experiments, but we're really producing them. It's an act of creation.
Creating them with atomic colliders, quantum calculation, and something passed on to him by his mentor, Dr. Glenn Seaborg.
He was a big believer in those little 35-millimeter slides, and he'd take a graduate student to run the projector for him.
One of those students was none other than Ken Moody. That's a younger Ken there. For 30 years, Ken has held on to this particular slide. Seaborg's map, a mythical place the elements of the periodic table inhabit. And it's here where our story begins.
Where uranium and thorium dwell, the end of the nuclei that exist in nature.
Number 92, uranium, is the last of the naturally occurring elements. This is as far as the stars got. But Glenn Seaborg thought he could pick up where the stars left off, actually creating elements, and he did. Marching up the periodic table, creating elements 94, 95, 96, 97, 98, 101, and 102. He won a Nobel Prize for his pioneering work and created more elements than any human ever had. And then he could go no further.
Even Seaborg ran out. The process by which he was making these, he and his whole large team by this point, that way of trying to add in more protons to a nucleus, that route finally dried up.
David Kaiser teaches the history of science at MIT.
What Seaborg had been able to do, and many colleagues by this point, was sort of go step by step, add in one new nucleus at a time, by just going literally baby steps.
How exactly do you take baby steps? Let's start at the beginning. We'll take a trip and fly into an atom, past the electrons into the nucleus. In a science where you never see what you're working with, a lot is left to the imagination. So first, let's meet some protons. For our purposes, represented by these guys.
All positively charged, and we all remember from science class in high school that two positive charges repel one another.
With this repulsion, how do any of the elements stay together?
The protons feel a different sort of force as well at the same time. It's a different origin, a different type of force between them, and that's a specifically nuclear force. It's called the strong force.
We'll show this as a bungee cord.
And that really is how this force behaves. If they try to pull apart, it'll pull them back together. It's an attractive, coming together sort of force. But like a bungee cord, it only works over a certain distance. If you try to stretch it too far, that cord will break.
That repulsive force wins.
And that's where this guy comes in.
Hello.
He is a neutron.
I went to school with an awful lot of neutrons. This is a fellow who comes equipped with bungee cords like the proton.
But unlike the proton, he has no charge, no inclination to push anything away. He just sort of sits there, neutrally. His bungee cord does the work. So, throw him in between a pair of struggling protons, hook up his bungee too.
The neutron provides some remediation of the hostility of the protons, and they can survive.
Up to a point. By the time he got to element 102 with 102 protons in the nucleus, Seaborg began having problems.
Even if you add in more bungees, they might keep this cluster together here, they might keep that cluster together there, but keeping a whole big thing together, that no longer is going to work. The pushing away force starts to win.
And there was another problem. Seaborg found the more protons he added, the shorter the atom survived. From billions of years down to thousands, days, hours, minutes.
Even much less. Sometimes thousandths of a second. If you're lucky, often it's millionths of a second. So these things will fall apart literally in less than a blink of an eye.
Seaborg came to see himself surrounded by a cruel and inhospitable ocean that tore his atoms apart. He called it a sea of instability.
The sea that they didn't know if they could cross or not. That's what was inspiring and really teasing or pushing Seaborg, and in fact many of his students and colleagues, to see could they go beyond this end of the known world? Could they go beyond where this peninsula seemed to stop?
Then in the mid-1950s, theorists presented a radical new concept of the nucleus.
There became lots of evidence to show there's a tremendous amount of very stringent, strict ordering that goes on inside the nucleus.
We're used to looking at diagrams where the nucleus is shown as a little ball with a plus sign in it, and the electrons travel in rings which are well-defined orbits. The nucleus is the same way. The protons and the neutrons can be treated as forming structures. You can think of it as rings.
And so in fact there are these configurations where the protons can line up in a special way in these sort of ring structures that will give a greater degree of stability to the nucleus as a whole than if there had been in some other random or messed up order. And same thing happens with the neutrons.
Just like the electrons that orbit the nucleus, the stability of the nucleus depends on how full these rings are. When you have just the right number of protons,
That is a configuration which we consider magic.
And just the right number of neutrons as well? That's called doubly magic.
So what's so magical about that? These magical numbers of protons or neutrons are such that you have the maximum stability.
That is a very strong nuclear configuration.
Theory predicts that element 114 should have this kind of doubly magic nucleus. So it should be, despite its tremendous size, incredibly stable. Seaborg would have to change his approach.
Don't add one particle at a time, add 20 particles at a time, add 40. And so that's like slingshotting over that sea instead of trying to march across it step by step.
And Glenn saw this as a giant leap across a sea of instability of things that you couldn't make to an island sticking up out here.
An island of stability.
So that was what was motivating Seaborg. Could you jump this inhospitable sea to get to this, what he hoped would be a magic island, an island of stability? Way up here, where you have all the way up to 114 protons and 184 neutrons. That was the next spot, they thought, where you'd have this sort of magic stability, both a filled ring of protons and, crucially, a filled ring of neutrons.
Where these huge atoms might last long enough to hold in your hand, to look at. Something new in the universe.
How badly did he want to get to the island of stability?
He wanted it bad. He really did.
And tried for 30 years?
Yes, basically, yes. We all thought that if he could discover super heavy elements, that we could get him a second Nobel Prize.
So how would Ken realize this dream and leap to element 114? Well, plutonium has 94 protons. Calcium has 20 protons. Add them together and voila, 114. But how exactly do you add atoms together?
You have to accelerate them at one another very, very fast.
You're throwing them at each other.
Throwing them at each other. You can almost think of it as bowling. Each calcium ion is a bowling ball. And as the calcium approaches the target, it sees a set of plutonium pins. And there are an awful lot of gutter balls. The calcium just misses the pins completely. We will put somewhere between 10 to the 18th and 10 to the 19th balls through a target. 10 billion. There's that one sweet spot there. If the calcium hits the thing, you get the element 114 strike. The calcium and the plutonium fuse, and you have an element 114 that survives.
Did they make it to the island of stability? Almost, but not quite. In 1998, Moody's team, in cooperation with Russian scientists, was able to bowl the magic number of 114 protons, but fell short of the 184 neutrons needed to achieve that double magic. In other words, while they still hadn't landed on the island of stability, they were this close, just at its shores, and that was no small feat.
I said to myself, I have to call Professor Seaborg and I have to talk to him. One of the great disappointments in my life was we couldn't have done that experiment 2 months earlier. He never knew about the result. He had had his stroke. He passed away a few weeks later.
Never knowing his magical island had been sighted. With Seaborg gone, Moody now continues the hunt for element 114's missing neutrons.
We're 10 neutrons short of where the maximum effect should be.
And those neutrons mean everything.
Big difference. The difference between existing and not existing.
Those neutrons may hold the answer to how long it might last.
Whether we're dealing with something that's very long-lived, like on the order of the age of the universe, or whether we're dealing with something that's minutes or hours.
But even minutes or hours is long enough to see, touch, and study.
I mean, a chemist's eyes light up because you can start thinking about doing all the chemistry experiments in the world.
Experiments to reveal what its properties might be. Perhaps a material with uses we haven't even dreamed of.
Maybe a ball of gas, actually. There are some predictions that think that it's actually a gas.
It could be a really heavy metal.
The periodic table says it should be a heavy cousin to lead and tin.
That would be very exciting because then we could prove that periodicity is, the chemical properties continue to extrapolate as you expect from the periodic table.
We would learn a tremendous amount of just basic nuclear physics. There's still these questions that we just can't figure out until we can make the stuff study it, and ask these questions in the laboratory.
One thing is certain, we will have something the stars did not leave behind. If only we can get to that magic island.
We think it's there. Can we get there? Can we plant our flag in the sand?
Maybe Ken Moody can.
That's the mystery of the island of stability.
There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Okay, we talked about bungee cords, that stretchy force that binds protons and neutrons. They're kind of like springs. Of course, what's great about springs is their flexibility. With some effort, I can stretch it, or I can make it smaller, at least for a little while. But it always bounces back to a certain predetermined size. Well, according to some researchers, people might be like this too. No matter how hard we struggle to lose weight, our bodies will keep bouncing back to about the same size. And as David Duncan reports, that size might be predetermined by our genes.
We are what we eat, and as we eat more and more, many of us gain weight we'd rather not have. But for some people, like Teresa Godfrey, the compulsion to eat is a lifelong struggle.
I try and control it as much as I can, but there are days that I cannot control it and I just eat and eat and eat and eat, and I don't know when I'm full, really. And I'm aware that I'm doing it, but I can't stop it.
Since childhood, Teresa has faced ridicule, embarrassment, and blame for being overweight. So is her only son, Jake.
Parents in the playground used to look over and look at me because I'm big, Jake's big, and just thought that we sat there all day and ate food, basically.
I was just going to ask you a few questions.
Patients like Teresa and Jake have had really a very tough time from a very young age. They've often been blamed for being overweight and obese, and it's amazing how we fail to see that actually being overweight and being obese can be due to a biological reason, can be due to your genes.
Suppose you could prove that for certain patients, it's not lack of willpower that causes obesity, but the lack of a chemical inside the brain which tells us to stop eating. That would be no surprise to Jeffrey Friedman, an obesity researcher at Rockefeller University in New York City. Friedman believes that for each of us, eating behavior is, to a large extent, hardwired by our genes.
What makes some people weigh 350 pounds and other people 150 pounds, to a very large extent, those are genes. And each of us are predetermined to be at a particular weight. Some people heavy, some people thin, most people in between.
So we have very little control over our weight, that there's a set point.
The set point defines a range for each person, and people can operate comfortably within that range. But the further one wants to deviate away from the set point in either direction, the more difficult it becomes. So that if you're at your stable weight and you want to lose 50 or 100 pounds, it is very, very difficult over the long term.
I lost 35 pounds in between 8 and 9 months. I found it very difficult, but did lose it. But it went back on. As soon as you stop dieting, it just goes straight back on.
For obesity, the evidence from a number of sources would suggest that it's 70 to 80% genetic, which is the highest hereditability that's been recorded, with the possible exception of height.
20 years ago, Friedman began experiments to uncover the genetics behind the hunger drive, trying to discover why certain lab mice are born with such a compulsion to eat that they become almost too fat to walk. Then, in 1994, Friedman and his collaborators made a groundbreaking discovery. These obese mice lacked a previously unknown hormone which signaled the brain to stop eating. Friedman named it leptin, after the Greek word for thin.
Leptin is a hormone made by your fat that circulates in the blood, that then sends a message to your brain reporting how much fat you carry at a given point.
The 5 milligrams of leptin in this bottle are 10 times the amount that can circulate in our bloodstream. where it acts like a thermostat to tell the body if it's starving or if it has enough fat to survive. How it works becomes clear when you see an animal genetically altered to produce no leptin at all.
You'll notice a few things about these animals. One, obviously, this animal is a lot larger or heavier. That animal is moving around everywhere, and this animal hardly moves at all. The only difference between these animals is a defect in a single gene, the gene that encodes for this hormone leptin.
And how does this relate to humans?
Humans have the same hormone, and when humans are lacking this hormone leptin, as is this animal, they too become massively obese and eat more. It turns out that this animal, because it lacks leptin, never gets the signal that it has sufficient fat and thinks it's starving. Now, if you were to give this animal leptin injections, replace the leptin it can't make on its own, they eat less, they lose weight, their fat content goes down.
Friedman's discovery created a sensation. Was this the holy grail for the overweight? A possible cure for obesity?
I remember precisely the day I read the Friedman paper, and the hairs on the back of my neck stood up, because I thought, oh, my word, this is a real insight into how body weight is controlled.
Unfortunately, when leptin injections were given to obese human patients, most of them did not lose significant amounts of weight. Still, Stephen O'Reilly, director of the obesity clinic in Addenbrooke's Hospital in Cambridge, England, believed that Friedman's discovery held an important key to human appetite, if he could understand how leptin worked.
Leptin does something to the brain. It suppresses appetite. It does it through a series of steps.
Once leptin reaches the brain, it turns off cells that increase appetite and turns on cells that decrease appetite in a dual action that suppresses hunger. A central switching component in the leptin process is the melanocortin-4 receptor, or MC4R, which receives and passes on the message to damp down hunger. If these receptors are altered by genetic mutation, their surface becomes malformed, unable to process the message to switch off appetite.
It will be very difficult to be a patient with one of these mutations. Try to get slim, and when your brain is screaming, you are hungry, you must eat.
You're just ravenous and you just have to eat it. And you can't stop. Some days you can't stop eating and you're on and on and on and on and on.
So you just eat anything until you're just full up, and then you regret it. It's like it just takes over you.
Until you actually physically begin to feel sick. And then you think, well, why did I eat all of that food? I didn't really want that. Why did I eat it?
Just head at this end.
8 years ago, Teresa Godfrey came to the obesity clinic in Cambridge searching for answers.
They've always known that there was some reason why they were always hungry. They've always thought there was some reason why they gain weight more easily than others. And effectively what we're able to do is to provide them for an explanation for that.
The new scientific breakthrough is understanding the gene that codes for the MC4 receptor. Teresa's gene has a mistake that causes her receptor to grow incorrectly.
When we actually look at the gene in the lab, what we find is that one particular one of those building blocks is actually different. And that's enough to stop this gene making a receptor that works.
Sadaf Faruqi extracted Teresa's DNA from a blood sample, then put it through a process to isolate the gene that encodes for her MC4 receptor.
And I think when MC4 is done, we need to think about which other genes might be relevant to these patients.
This gene was then amplified and inserted into a living cell in Faruqi's lab, which then grows Teresa's receptor in a flask.
And when it's in those cells can then be grown up and can actually behave in the test tube as if they were in Teresa's body. So essentially, in this flask are some cells which grow up and express Teresa's MC4 receptor on their surface. We add the hormone that normally activates the receptor. So basically, the hormone should dock on the receptor and give us a readout.
A normal MC4 receptor reads out 100%, but Teresa's malformed receptor reads out 0.
So Teresa's receptor is really non-functioning.
Measuring Teresa's mutation has allowed the doctors at Addenbrooke's for the first time ever to use genetics to accurately predict how much a patient will eat.
Basically what we can show is that the defect in a single gene and a single molecule and how it behaves in the lab determines the amount of food people will eat at a single meal.
Hi, I've got your lunch here.
Thank you.
So you can have whatever you like.
We might find that a person who's of normal weight and whose MC4 gene is working normally might eat somewhere in the round of about 400 to 500 calories when allowed to eat freely. Teresa, and with Jake in fact, they would eat probably 2.5 or 3 times as much.
Dr. Faruqi phoned me and told me the results, and I cried on the phone because I was just so relieved. I cried for Jake, not for me, more so than anything else.
Jeff Friedman's discovery of leptin in 1994 was a phenomenal catalyst to not only my work, but the whole of the field. This was the first time that a real molecule truly was regulating body weight in mammals, and we went on then to show that obviously it was relevant for humans too.
How many people have this MC4 receptor problem, and how does it compare to other genetic disorders?
Our best estimate so far is that around 1 in 1,000 people carry a mutation in MC4 and are obese. That means that worldwide there'll be tens, if not hundreds of thousands of people with this disorder, so it's not by any means rare, and it's certainly commoner than some well-known genetic disorders such as muscular dystrophy or cystic fibrosis.
Do you worry that people will look at this and say, aha, it's not the Big Macs, it's genetic?
Clearly, if you eat fast food all the time and are very sedentary, whatever your genetic makeup, you're going to gain weight. Clearly, if you have genes that predispose you to gaining weight, you'll gain even more. So it's always a balance of the two. I think even people who are overweight or obese and don't have an MC4 gene problem, they will have other genes that are contributing to them gaining weight very readily.
Scientists are already identifying other genes that contribute to obesity. The hope is to create medications that can help people who have inherited these genes maintain a healthier weight. But until then, overweight people should try to maintain the lowest weight their biology will allow.
People should do what they can to improve their health, and that would include being at the lower end of their range, exercising, eating a heart-healthy diet. So I think we need to focus on what we can do and improve health to the extent of our ability, but not criticize people because they can't lose hundreds of pounds. It's their biology that makes it difficult to lose those hundreds of pounds, not some personal failing.
When I found out about the MC4R, it was a relief and a release to know that actually, yes, it's not all my fault and there's a reason for this happening to me. I just like to be as I am now. I've accepted the way I am. If you would say to me, would you rather win the lottery or would you rather find out about MC4R, I would say MC4R any day. You can keep your money.
Know the popular image of artists, painters, writers, performers. They're creative but undisciplined. And then there's the scientist, analytical, methodical, obsessed with accuracy. But whether these cliches are right or wrong, sometimes the artist and the scientist are more alike than you think. Check out this guy.
At the sound of Maria's name, a shiver began in Henderson's chest that scurried over every inch of his skin. He felt as though he'd been heated over glowing coals, then dunked into an ocean-sized bath of ice water.
Meet Carl
Yanyama.
Yanyama.
Yanyama, yep. It's Italian.
He's a successful writer of fiction, but he's also the same person who's been called one of the top 10 innovative scientists of America. How can he be both? His father was Emilio Yanyama. Born in Italy, he came to Detroit and he raised a son to be just like him, an engineer.
I ended up following pretty closely in his footsteps. We shared definitely an interest and a love for physics and math.
I always knew he had a mind like my father. They used to go to computer clubs together, exchange software, and he took drafting classes.
And Carl did some experimenting when his father wasn't looking.
Friends and I would do various experiments with combustion, but nothing too serious. No felonies.
He would light tennis balls on fire and throw them down the driveway.
Uh-oh. I knew I shouldn't have given you her name.
But all those experiments clearly paid off because Carl went to MIT, where he stayed on to earn his PhD in mechanical engineering and is now a principal research scientist. And today, he's a top member of a team of researchers who are designing robots smart enough to understand their environment. Their algorithms will make it easier for robots to navigate through truly difficult terrain and enable NASA to explore parts of Mars scientists can only dream of reaching today.
Robots right now are pretty dumb. They have a hard time understanding if something is a bush compared to stone. For wheeled robots, the danger is always that you're going to drive somewhere, think it's a safe place to drive, and you end up getting stuck. And on Mars, you can't call AAA to tow you out.
As a researcher, I think Carl brings some of the best qualities you'd look for.
Paul Schenker manages the Robotic Space Exploration Technology Program for NASA at the Jet Propulsion Labs in Pasadena. NASA awarded Team MIT more than $1 million for research, overseen day-to-day by Carl.
He's very objective, patient, thoughtful in framing his problems. He also brings passion to his work.
But which work? Let's go back. Meet the other Carl.
Yanyema. It rhymes with dilemma.
His mother, Patricia Yanyema, was an English major.
My mother loved literature, so we had books in every room, in the laundry room, in the family room. Carl would lock himself in his room and just read and read and read.
Carl could also write. In fact, his minor at MIT was in writing. Fiction writing, which confused one of his advisors.
He said, "Oh, I thought you were studying friction."
Hard to believe, but true. Also true is that Carl's short story won a contest for fiction writing, not friction writing, held by Playboy magazine in 1998. And while he was writing his PhD thesis, he started to write his first book.
And I finished it the week after I finished my PhD thesis.
On the Nature of Human Romantic Interaction is meant to sound like a thesis. But don't be fooled. It's an award-winning collection of short stories about characters, many of them scientists, by the way, who fall in and out of love. Carl proves wrong the old assumption that science guys can only write science fiction.
I always refer to him as being whole-brained, using the totality of his brain. I see the dedication that he uses in science applied to his writing.
I don't think I know anybody who's certainly at that high a level in both those areas. It's rare.
Now, it would be easy to congratulate Carl for using more of his brain than most of us, which he clearly does. And it would be a little too easy to marvel at how Carl has managed to succeed at two professions that would seem to be complete opposites: science and fiction writing. But as it turns out, some of the very same skills Carl uses in scientific exploration come to his aid in, well, making stuff up.
In each discipline, you start with a blank page. You start with an idea. There are so many parallels between writing and research. I mean, I view each process as one of increasingly structured creativity.
Okay, so both a writer and a researcher have to be creative. But just ask any writer or any scientist, and they'll tell you creativity is meaningless without discipline. Before you can stare at a blank page or a screen, you must get your butt to the chair. And Carl does it day in and day out.
A lot of writing is just passing the time until something good comes along, and you don't know when that'll be. So to be safe, you should be in that chair as much as you can on the off chance that, a miracle will happen and the story will be born.
For Carl, it's a lot about patience and discipline. That's an important part of his process, I think. He does his hours, whether he gets 10 pages or one paragraph.
A lot of times I'm in the chair in the evening or in the early morning with my earplugs in so that I can hear all the characters' voices, and just typing either nonsense or typing an outline of a story or typing dialogue that may be good, maybe not any good. But when the story comes along and when you get that germ, that little spark, you feel it and you know it, and that's when the actual story writing process truly starts.
I think he's really efficient. He believes he's inefficient. Oh, it takes me so long to write. You write so quickly. And I'm like, dude, I'm not going to a lab trying to figure out how to get the machine to go over the big rock on Mars, okay? I'm having difficulty unloading the dishwasher, okay?
Both writing fiction and doing scientific research are pretty much full-time jobs. They're jobs that occupy you 24 hours a day. You're not a very good friend, lover, husband, wife during this period of months that you're consumed by a scientific problem. You're not very much fun to be around.
I definitely feel that Carl is with me when he's with me, but I do think that he thinks about his work all the time. Since we moved in together, and definitely since Sophia came, he has to be more structured in his work, and he has to set aside hours more. And I think he does that really well, and he does that in a very focused way.
But that structure, those hours, that's a lot of time spent alone.
Solitude is something, as a writer and a researcher, you have to be comfortable with. Writing is, really solitary, and research is kind of its little brother.
When you're solving the equations, you're usually alone, weeks and months. You will stop to eat meals.
The great untold secret about writing is it's incredibly lonely. You cannot do it, I can't do it anyway, with other people around.
And you have to be okay with that. Some people could never be okay with that. They just wouldn't enjoy the work because they would miss the human contact, or they would miss various aspects of being out in the world.
If I show up at my poker game and I've spent the day writing or trying to write, immediately my poker buddies are like, because I'm all, hey, how you doing, guys? All right, we're gonna get it. And they're like, have you spoken to anyone today? Have you talked with anybody? They know that, like, uh-oh, crazy lonely guy, here he is.
It's hardly a rational way to live.
Scientists are passionate about their work. They do it because they cannot not do it.
You get this little rush. You enter into the state where the time just seems to pass, and it's just the best feeling. And that's why you want to go back the next day and do it again, because of that feeling.
But can that feeling carry Carl through two intense careers? Alan Lightman chose to give up his research career in physics to become a successful novelist.
Both the science and the fiction writing are addictions. At some point, if he wants to be a scientist and he wants to be a novelist, one of those powerful forces is going to conquer the other one.
They'd met as first-year graduate students at the Michigan Engineering Institute, two aggressive young theorists who disagreed about Marx and Irish beer, but agreed that mathematics was a game, the most elaborate, wonderful game, like puzzling out riddles posed by God.
Right now I'm happy doing both. It's tiring, it's fairly exhausting, but it's satisfying. It's kind of the feeling I imagine after a runner has completed a long run. It's that pleasant, satisfied exhaustion. That's kind of my constant state. Thank you very much.
Exhausted and passionate, disciplined and humble, Carl Yang-Yama will continue to write and calculate using his entire brain. But to his friends, he's just plain old Carl, the walking algorithm for success.
If it were me, if I was doing this stuff, I would be like, dude, I've got a robot going to Mars. What did you do yesterday? And that was before lunch. Then I wrote a great short story in the afternoon. Then I hung out with my beautiful Swedish wife. What'd you do?
If that's not enough, the movie rights to one of Carl's short stories have been optioned by Hollywood to be produced by Brad Pitt. And now, back to that asteroid for some final thoughts. It's a curious fact of nature that severe asteroid impacts on Earth can devastate the ecosystem, leaving most life extinct. Countless tons of Earth's crust get cast high into the atmosphere, while soot from widespread fires cloaks the planet, knocking out the base of the food chain and sending a wave of extinction across the tree of life. Sounds bad? It is. But the loss of so much life also pries open fresh niches that allow new forms of life to thrive. For the famous KT impact 65 million years ago, the one that ended the reign of the dinosaurs, as much as 2/3 of all species were wiped out. But among those creatures that did survive, we find our mammal ancestors, a mere twig in the tree of life. But without dinosaurs to dine upon them, these early mammals could evolve into something more ambitious, like modern-day primates, like people. Asteroids. You can't live with them, and you can't live without them. And that is the cosmic perspective. We'd like to hear your perspective on this episode of Nova Science Now. Log on to our website and tell us what you think. You can watch any of our stories again, listen to podcasts, hear experts, and much more. Find us at pbs.org. That's our show. We'll see you next time.